August 14th, 1979, 9:45 Pacific Daylight Time. A McDonnell Douglas DC-10 sits at Gate 72, Los Angeles International Airport. The aircraft registration, N103AA. American Airlines Flight 139 to Chicago O'Hare International Airport. Captain Richard Thompson completes his exterior inspection, walking beneath the wing, examining the two General Electric CF6-6D turbofan engines mounted in underwing pods. Each engine produces 40,000 pounds of thrust. Each weighs nearly 9,000 pounds. Then he inspects the third engine, mounted in the base of the vertical stabilizer. The center engine's S-duct intake routes air from above the fuselage to the engine deep within the tail cone. A complex installation unique to the DC-10's configuration. First Officer Michael Barrett examines the main landing gear, 6 wheel bogies on each side, 12 main wheels total, plus 2 nose wheels. The DC-10's landing gear supports maximum takeoff weight, approaching 550,000 pounds. Flight engineer David Hayes checks hydraulic fluid levels, examining 3 independent hydraulic systems. The DC-10 operates with a 3-person cockpit crew, captain, first officer, and flight engineer. The wide-body competition, McDonnell Douglas developed the DC-10 in response to airline requirements for wide-body capacity on domestic routes. Boeing dominated long-range wide-body market with the 747, but airlines needed smaller wide-body aircraft for routes that couldn't fill 400-seat jumbos. American Airlines issued specifications in 1966. The aircraft needed to carry approximately 250 passengers, operate economically on transcontinental routes, use existing airport infrastructure without requiring facility modifications. McDonnell Douglas and Lockheed both responded. McDonnell Douglas proposed the DC-10. Lockheed proposed the L1011 TriStar. Both chose 3 engine configurations for similar reasons. More thrust than twins could provide with 1960s engine technology, better fuel economy than 4-engine aircraft. American Airlines ordered DC-10s in February 1968. United Airlines followed with orders for both DC-10 and 747. The DC-10 flew first in August 1970. Commercial service began in August 1971. Cockpit configuration. Inside the cockpit, Thompson settles into the left seat. Barrett takes the right seat. Hayes sits at the flight engineer station, a sideways-facing panel on the starboard side. The instrument panel displays analog gauges across both pilot positions, airspeed indicators, altimeters, attitude directors, radio-magnetic indicators showing navigation information. No flight management computer in this 1979 DC-10. Navigation uses inertial navigation systems, VOR, and ADF radio navigation. The autopilot can maintain heading and altitude, but requires active crew management. Hayes's engineer panel monitors all aircraft systems. 3 columns of engine instruments, 1 for each CF6. Fuel quantity indicators for 6 fuel tanks. Hydraulic system pressures. Electrical generation from 3 engine-driven generators plus auxiliary power unit. Passenger loading. Ground crew load 223 passengers today. The DC-10's typical configuration accommodates 270 in mixed-class seating. The wide-body cabin, 18 feet diameter, allows comfortable twin-aisle layout. The cabin cross-section uses 2-5-2 seating in economy class, 2 seats at each window, 5 across the center section. 2 aisles provide passenger flow. The lower deck cargo holds accommodate LD3 containers, standardized units that revolutionized air cargo handling. The DC-10 can carry substantial cargo in addition to passengers, critical for airline economics. The tri-jet layout. The DC-10's three-engine configuration reflects specific design choices. Two wing-mounted engines provide primary thrust. The tail-mounted center engine offers redundancy and performance advantages. The tail engine's S-duct installation presented engineering challenges. Air enters an intake on top of the fuselage, travels through a curved duct, reaches the engine mounted low in the tail cone. The duct must maintain smooth airflow despite the complex path. This arrangement keeps the tail engine's weight relatively low, reducing structural loads on the vertical stabilizer. But it complicates maintenance. Engine changes require more labor than wing-mounted engines. The DC-10 and L1011 chose different tail engine installations. The L1011 mounted its center engine straight through the vertical stabilizer. The DC-10's lower mounting in the tail cone created the distinctive S-duct. Engine start. Hayes initiates start sequence for engine number 2, the tail-mounted center engine. The CF6 uses pneumatic starting from the auxiliary power unit. Start switch engaged. The turbofan begins rotating. At proper RPM, fuel flow initiates. Ignition occurs. Exhaust gas temperature rises. The engine accelerates toward idle. The CF6-6D produces a characteristic high bypass turbofan sound. Most air flows around the engine core rather than through it. Quieter than earlier turbojets, more fuel efficient. Engines 1 and 3, the wing-mounted turbofans, follow in sequence. 3 CF6s now running at idle. Combined thrust at takeoff power, 120,000 pounds. Taxi and pre-takeoff. Thompson receives taxi clearance. The DC-10 begins moving toward the departure runway. The wide-body aircraft handles smoothly despite its size. Good visibility from the cockpit. Responsive nose-wheel steering. At the runway hold point, Hayes completes the before takeoff checklist. Flaps, 15 degrees. Stabilizer trim, set for takeoff based on weight and center of gravity calculation. Flight controls, full deflection check. Ailerons, elevators, rudder. 3 engines, all parameters normal. Today's gross weight, 460,000 pounds. Fuel load, 32,000 gallons, approximately 214,000 pounds. Enough for the transcontinental flight, plus required reserves. Takeoff performance. The DC-1010's performance varies significantly with weight and conditions. At maximum gross weight on a hot day at Denver's high altitude, the aircraft requires most of an 11,000-foot runway. Today at Los Angeles, sea level, moderate temperature, not at maximum weight, performance is comfortable. Calculated speeds. V1 decision speed, 155 knots. Rotation speed, 165 knots. V2 initial climb speed, 180 knots. Tower clears Flight 139 for takeoff. Thompson advances all 3 throttles to takeoff power. Hayes monitors engine instruments, ensuring equal thrust development from all 3 CF6s. The DC-10 accelerates. The swept wings generate increasing lift as speed builds. 100 knots, 140 knots. Barrett calls speeds. Thompson maintains runway centerline with rudder inputs. V1, committed to takeoff. Rotate. Thompson applies back pressure to the control yoke. The nose lifts. The main gear remains on concrete briefly. Then the wing's lift exceeds weight. The DC-10 climbs at 1,800 feet per minute. Gear retraction. Barrett raises the landing gear handle. 12 main wheels and 2 nose wheels retract into wheel wells. Doors close to maintain aerodynamic cleanness. Climb to cruise. The DC-10 turns eastbound, following the departure procedure. At 10,000 feet, flaps retract to clean configuration. Airspeed increases toward climb schedule. Hayes monitors engine parameters during climb. The CF6 turbofans operate efficiently, but the tail engine runs slightly warmer than wing engines due to the S-duct installation. The curved inlet creates minor pressure losses. The DC-10 continues climbing. 20,000 feet. 30,000 feet. Rate of climb decreases as altitude increases and air density decreases. At 39,000 feet, Thompson levels the aircraft. Hayes reduces power to cruise settings. The three CF6s settle into long-range cruise operation. Cruise speed, Mach 0.82, approximately 530 miles per hour, true airspeed. Fuel consumption, approximately 14,000 pounds per hour at this weight and altitude. Systems management. The DC-10's hydraulic systems require active management. 3 independent systems, each powered by one engine-driven pump. If one system fails, 2 remain. Critical flight controls receive power from multiple systems for redundancy. The cargo door system uses hydraulic operation. Proper closure and locking is critical. Early DC-10s experienced cargo door problems when doors opened in flight, causing rapid decompression and structural failure. American Airlines Flight 96 in 1972 survived such an incident. Turkish Airlines Flight 981 in 1974 did not. 346 fatalities. McDonnell Douglas modified the cargo door system after the accidents, adding additional locks and warning systems. By 1979, the design changes have been incorporated fleet-wide. Navigation across America. The flight plan follows standard transcontinental routing. Navigation primarily uses inertial navigation systems, 3 independent units calculating position through internal gyroscopes and accelerometers. The crew cross-checks INS positions against VOR radio navigation. The DC-10 carries dual VOR receivers, ADF for non-directional beacons, and DME for distance measuring. No GPS, no flight management computer. Navigation requires active crew participation, monitoring multiple systems, cross-checking positions, updating navigation computers. Hayes manages fuel distribution during cruise. The DC-10's 6 fuel tanks distribute throughout wings and center fuselage. Proper fuel management maintains center of gravity within limits as fuel burns. Crew operations Thompson and Barrett share flying duties during the transcontinental flight. One pilot flies the aircraft while the other handles radio communications and monitors systems. They alternate roles to maintain alertness. Hayes continuously monitors the engineer's panel. Engine parameters, fuel quantity and flow, hydraulic pressures, electrical generation, pneumatic systems providing cabin pressurization and air conditioning. The 3-person crew represents standard wide-body operations in 1979. Later aircraft will eliminate the flight engineer position through automation and improved cockpit design. But in 1979, the engineer's role remains essential for managing complex aircraft systems. Mid-continent position. 2 hours into the flight, the DC-10 crosses Kansas. Fuel consumption tracking as planned. All systems operating normally. Weather at Chicago acceptable. The cabin crew has completed beverage service. Passengers settle into the flight. Some work, some read, some sleep. The wide-body cabin provides more comfort than narrow-body aircraft. More overhead bin space, wider seats, better air circulation. The DC-10 helped establish passenger expectations for wide-body comfort on domestic routes. Descent planning. 300 miles from Chicago, Thompson receives clearance to begin descent from cruise altitude. The descent requires careful coordination with air traffic control and adherence to arrival procedures. Thompson initiates descent, reducing power, lowering the nose slightly. The DC-10 descends at approximately 2,000 feet per minute. Hayes monitors engine parameters. The CF-6 handles power reductions smoothly, but rapid temperature changes require monitoring. Approach to O'Hare. At 20,000 feet, Chicago approach control vectors Flight 139 into the arrival pattern. The crew configures the aircraft for landing. Flaps extend in stages. 5 degrees, 15 degrees, 28 degrees, 50 degrees only during final approach. Each extension increases drag and reduces stall speed. Landing gear extends. The 12 main wheels and 2 nose wheels deploy, creating significant drag. 3 green lights confirm all gear down and locked. The DC-10's approach speed depends on landing weight. After burning fuel during the transcontinental flight, the aircraft weighs approximately 340,000 pounds. Final approach speed, 145 knots. Landing O'Hare's runway 32L extends 13,000 feet, more than adequate for DC-10 operations. Thompson flies the visual approach, following the glide slope. Barrett monitors airspeed and configuration. Hayes confirms all systems ready for landing. The runway threshold passes beneath. Thompson reduces power to idle, initiating the flare. The DC-10's landing technique requires smooth control. The swept wings' lift characteristics change during the flare. The main gear contacts the runway. Firm but controlled touchdown. Thompson deploys thrust reversers on all 3 engines. The reverser cascades redirect exhaust forward, providing substantial deceleration force. Wheel brakes supplement the reversers. The DC-10 slows to taxi speed within 7,000 feet. The operational reality. The DC-10 served airlines for over 3 decades, from 1971 to the early 2000s. Through economic cycles, through fuel crises, through changing passenger expectations. The aircraft proved economically successful despite its troubled early history. Airlines operated DC-10s on transcontinental routes, international routes, and medium-range services where wide-body capacity made sense. The trijet configuration became obsolete as twin-engine technology improved. Modern high-bypass turbofans provided sufficient thrust for 2-engine wide-body operations. The Boeing 767 and Airbus A330 eventually replaced trijets on most routes. Better fuel economy with 2 engines instead of 3. But in its era, the DC-10 filled a crucial role. It brought wide-body economics to routes the 747 couldn't serve efficiently. It competed directly with the L-1011, a technically superior aircraft that ultimately sold fewer units due to Lockheed's financial problems and later market entry. Safety record. The DC-10's safety record cannot be separated from its operational history. Early accidents, particularly Turkish Airlines Flight 981 and American Airlines Flight 191 in 1979, created public perception problems that persisted throughout the aircraft's service life. Flight 191 at Chicago O'Hare in May 1979, just 3 months before this flight, killed 273 people when an engine separated during takeoff, severing hydraulic lines and making the aircraft uncontrollable. The accident resulted from improper maintenance procedures, not design flaws, but it reinforced negative perceptions. The DC-10 ultimately compiled a safety record comparable to other wide-body aircraft of its era. But early accidents and the aircraft's association with those tragedies shaped its reputation permanently. Evening at O'Hare Flight 139 taxis to the gate. Ground crew position jetways. Passengers begin deplaning. Thompson, Barrett, and Hayes complete the shutdown checklist. 3 CF-6 engines wind down to silence. Hydraulic systems depressurize. Electrical power transfers to ground sources. The transcontinental flight is complete. Los Angeles to Chicago in 3 hours, 52 minutes. Tomorrow, the same DC-10 will fly another route. Different crew. Same procedures. Same tri-jet configuration that defined an era of wide-body aviation. The DC-10's place. The DC-10 that proved wide-body economics worked on domestic routes. That competed in the market Boeing and Lockheed also pursued. That suffered through well-publicized accidents, but continued serving profitably for decades. Not through revolutionary technology, through solid engineering applied to clear market requirements, through crews who flew these aircraft professionally despite public concern, through airlines that operated the type successfully long after early problems were resolved. The aircraft demonstrated both the promise and the challenges of rapid wide-body expansion in the 1970s. It showed that aircraft design involves not just engineering, but also quality control, maintenance procedures, and regulatory oversight. Lessons learned through tragedy. The tri-jet that carried millions of passengers safely. That proved economically viable despite 3-engine operating costs. That served until better technology made it obsolete.